So if you have a circle and I take 2 points on that circle, let's call those points A and B, then that is called, you could call this an arc. And if we had the center of the circle, this would form an angle. And whatever this angle is, let's just say that, oh, this is maybe like 80 degrees, then we could also call this arc 80 degrees. And we could write this as the measure of AB, and we put a little curve over the top, and that stands for arc. The measure of arc AB would be 80 degrees. And this is a review. We've talked about this before. What I want to talk about today is what if I took these same 2 points and instead of connecting them to the center of the circle, I connected them to a different point on the circle. Let's call that point D. And let's ignore this for a minute so it doesn't clutter the diagram. So we have this arc that's 80 degrees, and I connect its endpoints to a different point. Again, instead of being connected to the center, I connect them to another point. The angle we form here is angle D, and angle D is called an inscribed angle. And it is the angle that is inscribed on arc AB. And what if I told you that I know that if that arc is 80 degrees, that this angle has to be 40 degrees? Wait, what's going on here? Am I saying that this angle has to be exactly half of that arc measure? And that's exactly what I'm saying. In other words, another way to think about it is if you have the center of the circle and we connect that, the angle formed connecting that is always exactly double the angle formed when you connect it to the edge. So now you might hopefully be wondering why, because that's the big question that's always interesting in math. Why? Why would this angle have to be exactly half of that arc measure, exactly half of the angle you get when you connect it to the center? Well, let's go to a specific case first. So specific case, what if we had exactly half of a circle? So we're going to start out with a diameter. So what if we have a diameter? So this goes through the center. It's the diameter of a circle. Now, I could call these endpoints A and B. What if I pick, kind of randomly, any other point on this circle? Maybe I just pick a point like over here. And I could call that point D. So let's think about what that would mean. If I connect the A to D and B to D, we have now formed an inscribed angle. This inscribed angle right here. And my question to you would be, based on what we just talked about, what would we predict this angle has to be? Well, think about what is the arc measure we're talking about. The arc from A to B is around the circle like this, right? And the central angle we're talking about here is actually the diameter. It's a straight line. So that would be a 180 degree angle, which would make this a 180 degree arc. So if we apply what we just talked about, we would say that this should be 90 degrees. And apparently my phone found something on the web. So it must have thought I said Google or something. So we have to say that this would be 90 degrees. But that's, again, what we think should be true if this pattern works. But let's actually prove it this time. Let's prove that that's 90 degrees. So to prove that, we're going to draw another line. So if I connect point D to point C, I'm connecting a point on a circle to the center of the circle. And that would be a radius. And it has a certain length. And I'm going to mark that length with that marking. I want you to look at this diagram and think, can you find any other lines in this diagram that should be marked the same? In other words, can you find any other radii? Giving you a second to think, you should be noticing one from A to C. That's a radius. And you should be noticing that from B to C is a radius. Anytime we connect the outer edge of a circle to the center of the circle, we form a radius. And the definition of a circle is all points on the edge of the circle to the center are the same length. So these three all have to be the same length. Now I want you to look for something. I'm going to call this angle, the angle right here, I'm going to call angle X. So let's call this angle X. Can you find another angle that has to be the same as angle X? Giving you a second to think, and I'm hoping you spotted one right here. You can always pause the video if you want more time to think. So why does that have to be the same as that? I'll give you a second to try to justify it. Again, you can pause the video if you want more think time. And it's because this is an isosceles triangle. Two sides the same length, and we've proved in the past that in an isosceles triangle, the base angles are always congruent. So these angles would have to be the same as each other. Now, I'm going to grab another color. Let's go with green. And I'm going to call that angle Y. And do you see anything else that has to be the same as angle Y? Hoping you're spotting it here. Once again, we have an isosceles triangle. And in the isosceles triangle, the base angles have to be congruent. So these both have to be the same. So the angle we're actually thinking about in this problem is this one, angle D, which is now split up into an X and a Y, meaning that angle D is X plus Y. But does that help us? Does that prove that it's 90? Well, I want you to look back at our bigger triangle, triangle ADB. So we're looking at triangle ADB, and think about its angles. It has angle Y, it has angle X, and it has angle X plus Y. So these things all added together have to equal what? What do all the angles in a triangle add together to be? Well, 180 degrees, right? So that's 2 copies of X and 2 copies of Y add together to equal 180 degrees. Okay, and remember that angle D is X plus Y. Angle D is X plus Y. So think carefully about what this means. 2 copies of Y and 2 copies of X equals 180. So what would 1 copy of Y and X added together be? It would have to be half of 180. It would have to be 90. You could also just divide that equation by 2 if you want to do this with algebra. So we just proved that X plus Y is 90. So we proved that angle D is 90 degrees when the arc measure that it connects to is 180 degrees. So in this specific example, we've proved that the inscribed angle is half of the arc measure. And the other cool thing that we've proved here that's kind of useful just on its own is that anytime you have a circle and you have a diameter, you could pick another point on the circle, connect to it, and you will always get a right triangle, no matter where you put that, which is kind of neat. You could also think about, what if you took string and you connected a string from here and here, maybe you put nails there, and you tie a string to it, and then you put your finger on the string and you're holding it there. You've got a 90-degree angle, but you could slide your finger along, and like wherever you stop your finger, you're going to get the string connecting up there, and that's always going to be a 90-degree angle. All right, but let's go back to the bigger picture that we were trying to prove here today. We're trying to prove that anytime we make an inscribed angle on an arc, we always get half the measure of the original arc. We just proved that works if you happen to start out with a diameter. But can we prove that it works all the time? Well, I'm going to use this diagram to get one more fact that's going to really help us out here. So it's really the same thing we just proved, but what I want us to look at it a slightly different way. So we have here actually an inscribed angle Y, which is an inscribed angle on this arc right here. arc AD. And the central angle from A to D would be, if we connect those to the center, point C. And so if what we're trying to prove is actually true, this angle right here would have to be double this one. It would have to be 2y. Can we prove that it's 2y? Well, I want you to think about it. What is x plus question mark? X plus question mark. It's a triangle, right? So that would have to be 180 degrees. Well, x plus x is 2x. And it does add with something to get 180 degrees in this diagram. What does it add up with? 2x's plus 2y's equals 180. So that would mean that this does have to be 2y. And remember, that's the same thing as the arc measure out here. So we have this arc, and we have this inscribed angle, and that's why this arc measure is 2y. We could also do that right here. So if we actually focus on the red angles here, I have angle x right here, and you could think of that as an inscribed angle from arc DB. And again, if our reasoning works out, this needs to be half of this. And remember, this arc measure is actually measured at its central angle when I connect these 2 points to the center. So what I'm saying here is, what is this question mark? If our theorem holds out, our theory, our conjecture holds out, this needs to be 2x. And let's check if it actually is in this diagram. Well, we have in this triangle right here, see this isosceles triangle, we know that y plus question mark has to be 180 degrees. Y plus question mark has to be 180 degrees. In other words, 2y plus something has to be 180 degrees. Well, that something in this diagram has to be 2x, because that is the thing that we add to 2y to get 180 in this diagram. So that means that this has to be 2x, which again means that this arc is measured at 2x. So in this diagram, all the stuff seems to be holding out. But what if we started out without having a diameter? Well, I want you to think about this relationship that we just proved here, where if we do have this diameter, if that's y, then that's 2y. If that's x, then that's 2x when we have the diameter. Let's start out where we don't have a diameter. So new picture where we don't start out with a diameter. The trick, by the way, is going to be to add a diameter into the problem. So we have a circle. I'm going to redraw the outside there. So we have a circle, and we have well, let's go with 2 points, A and B. And once again, what we're trying to prove here is if I just pick some random-ish point over here, let me go here, okay? So we'll go with this one. So we'll call that point D, that if I connect these together, I want to prove that this angle is exactly half of this arc measure, okay? Remember, this arc measure is actually, if we take the center of the circle, which we can call C, and we connect these 2 points to it, this angle right here. So what we're really trying to do is prove that this angle is double this angle, or the other way around. This angle is half of that angle, because that angle is what we mean by the arc measure. So this time, we're not starting out with having to have a diameter at the beginning. This is really 3 arbitrary points on the circle. Okay, well, what we're going to do is actually just turn it into the same diagram we had before. What if I connect this point to the center? And then I connect this point all the way through to form a diameter. So we now have a diameter in this problem when we didn't before. What we actually have now, if we just look at half of this picture, is the same diagram we just had when I started out with a diameter. Notice that if I just think about this as one of my other points, that this would be a diameter with a point. This would be a right triangle. We have my radius, another radius. It's the same diagram we had before. And in that diagram, we proved that whatever this angle is, let's say it's y, and it was on a diameter, I proved that this one had to be 2y. You can rewind the video and look back at the last diagram and see if you notice the connection here. This is our right triangle on our diameter. If that's y, then that's 2y. And then, what if we had this angle, which I'm going to call x? Now, these two don't have to be the same because this diameter is not necessarily splitting this angle exactly in half. But whatever that is, notice once again, if we look at this half of the diagram, we have a diameter with a point, and once again, we could form a right triangle. It's that same situation. X is going to be half of this. This would be 2x. Again, if you want the proof of that, look back at the proof we did where we started with the diameter, and you'll see it's the same situation. So now look at this situation. Angle D is x plus y, right here. And we know that the arc measure AB is the same thing as its central angle right here. And the central angle here is 2y plus 2x. Notice that x plus y is going to be exactly half of 2y plus 2x. So that once again proves that the arc, the inscribed angle, is exactly half of the arc measure. Okay, so that's a whole bunch of proof stuff. Let's go back to what is it that we just proved? So what did we actually prove today? We proved that when you just start out with a blank circle, if you pick any 2 points on that circle, you can call them whatever you want, but I'm going to call them A and B. So we start out with 2 points on the circle. We call them A and B. There's an arc measure that goes between them. It's the same as the angle that you get when you connect it to the center. And if we pick another point on the circle and we connect these to it, what we proved is that the measure of angle D is half the measure of the arc AB. So, for example, if we knew that AB had a measurement of, let's call it 70 degrees, so if AB, the measure of arc AB equals 70 degrees, then the measure of angle D would equal what? It would be 35 degrees because it would be half of that. We could have also reversed this problem. If we had that this was 35 degrees and the question was, what is that? That would have to be 70 degrees. Another interesting thing is if I put a point over here, called it like F, I could connect these 2 points. And if they're connected to the same 2 points, again, this would have to be 35 degrees. Because this is half of that, and this is half of that. They're half of the same thing. So I could connect it again here. And that would also have to be 35 degrees. So there's a lot of ways you can use this theorem. All right, so we've proved that the measure of an inscribed angle is half of the arc that it is connected to. I'll give you guys some problems to solve, and I'll give you solutions to them in the next video.